All right, good afternoon, everyone. Welcome to the final session of the conference. Glad you all stuck around. It's been a great conference. Just to get a sense, who here has been or currently is in an on-call rotation? All right, well, quite a few of you. Are any of you actually on call right now? Good, that's very responsible. So I'm sure many of you have a lot of stories to share about when you've been on call. We always fear those moments when we're woken up in the middle of the night and we're on call and there's some loud noise going off and we're just trying to figure out what's going on. And once we realize it's our pager, it's pager duty or whatever other service you use, that's when a little bit of fear sets in and you start to wonder, is this a false alarm? Or am I going to be up for the next 4 hours trying to figure out what's happening? Production systems are very interesting places. We, as someone earlier in the conference said, we design for the worst and hope for the best. And when we finally put things out in production, we're kind of like, please behave the way I expect you to. But once we kind of answer that page and we start digging into the problem, and we've kind of got our head into the issue. For me at least, it takes on this sense of I'm trying to solve a puzzle or unravel some kind of mystery. There's this process of discovery because we plan for failure, we try to make our systems robust, but when they fail, that means we've overlooked something. And there's something about our system that we don't fully understand. And so it's an opportunity to learn and to get new insight into our systems. So today I want to talk to you about some lessons that we've learned in scaling the Eero cloud, some of those things that have woken us up in the middle of the night, and some of the interesting insights we've gained from that. My name is John Lin. I am the Cloud Platform Manager at Eero. You can follow me on Twitter. It's great. I don't tweet, so I'm not going to pollute your timeline. Unfortunately, I was not the first John Lin on Twitter. Or you can reach me at john@eero. I thought about putting a biopic up here, but you can all see me, so here's a picture of my dog, and you can follow him on Instagram at ewalkrudy and get more pictures of him contemplating the meaning of life. So, how many of you know about Eero or own Eeros? Oh, awesome. This is great. For those of you who don't know what Eero is a product that we built to make sure you never have to worry about Wi-Fi again. It is what we call a whole home Wi-Fi system. And we've designed it to be very easy to set up, very easy to maintain, and to provide you reliable performance. Many of you probably have played network IT admin for your friends and family because you know how networks work and you know how technology works. We've tried to make Eero such that we say your grandmother can set things up and run it. We've done a lot of really good things with Eero. We've designed it from the ground up. We've designed our own hardware. We've done our own industrial design. We have beautiful mobile apps, and we have a cloud component. But you may be wondering, what is whole home Wi-Fi? How is this different than my current router? Whole home Wi-Fi is simply multiple access points in your home. We believe that the solution to our Wi-Fi woes is not a bigger, stronger, more intimidating looking router with lots of antennas, but actually to place multiple access points through your home where you need it the most. It's not always the case that your Nest thermostat or your Ring doorbell or your smart scale or all these other connected devices in your home are located conveniently around your wireless router. There's a lot of obstacles in a home. There's thick plaster walls. In the city, we have a lot of lead paint and chicken wire in this old construction. And some people have really big homes. They have outdoor patios, such great luxury. But it's hard to get Wi-Fi signal everywhere. You don't light your entire home with a single light bulb. You don't try to broadcast music throughout your entire home with a single speaker. So it doesn't make sense to try to cover your entire home with a single router if there's enough obstacles in the way. Homes are just becoming more connected, and we need to improve our infrastructure in the homes to support all of our connected devices. Fun fact, we did a study of the top 10 metro areas to see who had the most connected devices across all of our networks. Austin came in at number 1, averaging about 15 connected devices per network. So the Eero Cloud, like what does it do? How's it a part of this? The Eero Cloud is something that all of our devices talk to, and the service that it provides is to do a lot of coordination and configuration of networks. Distributed systems are hard. We know this on the service building side. Mesh networks are also distributed systems, and it's very hard to coordinate things across those. Here's kind of a snapshot of what our app looks like. You can see this home has 4 Eeros, they're online. There's 12 connected devices, and you can get information about your speed tests and how much data these devices are consuming. Another thing that the Eero Cloud does is make sure that your network is always up to date. You've all probably heard of the crack attack, the WPA2 security issue. That's huge. The WPA2 was thought to be like the secure way to prevent people from snooping on your network. Well, there was a problem there. This was announced on Monday. We had a patched firmware available on Tuesday. All your Eero customers here, if you open up your app, if you don't already have it, you can download the firmware now and from the comfort of your seat, update your network. But by this weekend, all Eero networks should be updated and secure. Just to kind of round out a picture of our tech, all of or majority of our backend services are written in Scala. We make heavy use of Play, Akka cluster. On the device itself, we run Python, Go, C. So now let me kind of get to the meat of this talk. I want to present to you a 3-step guide on how to DDoS yourself. And for each of these steps and these stages, we're going to discuss interesting failure scenarios that we've encountered at Eero, how we kind of discovered these problems and the interesting insights we got from them. And at the end, I'm going to try to give some advice about things that we did or things that you may be able to do to prevent these types of failures in your system. So like any good recipe, there's some ingredients, there's some prerequisites. And for this recipe, there's actually one really big prerequisite, or maybe you can consider it to be a few 100,000 prerequisites or ingredients. And that is a bot army. It's very hard to launch a distributed denial of service attack if you don't have many bots doing your bidding. Now, I want to say that bot army is really just a rhetorical device in this case. Eeros are not our bots that do our nefarious deeds. They are designed to behave in the best interest of our customers. Sometimes that's not always in the best interest of our backend services. Here's what these evil bots look like. They're actually very unassuming and pretty. But they are bots. I mean, they do things on very predictable intervals. They report network status and health. They report usage statistics that we can use to aggregate and give to our customers a view of how their network is behaving. They do this thing called heartbeat. And the heartbeat is one of the main mechanisms of how Eeros tell us, hey, we're alive, we're active, and by the way, is there anything for me to do? Do I need to run a speed test or update my firmware? So these Eeros are constantly heartbeating to us. And there are a lot of these devices. We've been fortunate to be very successful up to this point. And with great success comes great responsibility. Fortunately for us, success is a pretty manageable thing. We're not like Pokemon Go. We're not going to get 10 million new users overnight and suddenly taking down our system. We can only sell Eeros as fast as we can build them. So we can do a lot of really great capacity planning, anticipation around new people coming online. We have this luxury where we can think about what the next order of magnitude looks like and say, there's going to be these really hard problems at that next order of magnitude, but those, for us, are good problems to have because that means we've sold 10 times the number of Eeros that we currently have. To give you a sense of the good problems we have right now, our backend system processes around 5 billion requests a day. Across all of our customer networks, there are millions of connected devices, iPhones, tablets, Google TV, or Google Chrome devices, Chromeboxes. All these interesting devices that people have in their home to enrich their digital lives. And we make heavy use of Akka cluster on our backend. So we have millions of actors spread across several Akka clusters that provide different services. So we've kind of met our prerequisite here. We have this bot army. So the first step in our journey of DDoSing ourselves is to make this bot army work together. So I want to talk about synchronicity. Now, even though we've designed these devices to do things on very periodic intervals, we do not want them to do it all at the same time. That would be tragic. Like, we don't design our services to handle all the requests all at once and then sit around there kind of twiddling our thumbs, waiting for traffic. We'd really like everything to happen in a very even, distributed manner. Early on, we had some initial assumptions. We said, there's going to be a lot of randomness externally in our system. Not every user is going to plug their eros in at the same time. Not everyone is setting their networks at the same time. So all of these regular actions that the devices are doing should be uniformly distributed because people in their behaviors are uniformly distributed around the kind of the time intervals that we're thinking about. And for the most part, this assumption played out. Things came online, graphs looked really good, but in the wise words of Jeff Goldblum, life finds a way. In 1665, there was a scientist and horologist named Christian Huygens. An horologist is someone who deals with time. And he observed, sitting in his home, that he had these two pendulum clocks hanging from a beam, kind of like a reproduction of it here. And the odd behavior that he noticed was that these pendulum clocks would sway in synchronicity. They didn't always do that. So he said, why are these clocks ticking together? So being a scientist and wanting to explain this, he ran some experiments. He disturbed one of the pendulums, got them out of sync. But slowly over time, they came back to tick together again. By the way, he was the inventor of the pendulum clock. He theorized that this behavior was because these pendulums were exerting some kind of unseen force to him on each other. And he thought that this beam that the clocks are hanging from is what's transferring this force and enabling them somehow to affect each other and to get into sync. He called this phenomenon the sympathy of two clocks. Fast forward 350 years later to our modern day, we have our own set of pendulum clocks, so to speak. We have these devices that are heartbeating to us at very regular intervals. And again, our assumption was heartbeats are not going to be synchronous. They're going to be uniformly distributed. People set up their networks and turn on their eros at different times. That would be crazy. And that assumption, again, played out for a little while until we noticed some odd behavior. I'd like to take you through this process of discovery we had. Just to give you a sense, this is what a normal heartbeat distribution graph looks like. This is a kind of a recent snapshot from one of our dashboards. It's very boring, and we love boring metrics like this. This means everything looks great. But in the beginning of our service, after a few weeks of shipping to our customers, things weren't so boring. Now, this is not a graph of heartbeat counts. This is a graph of latency. We're measuring latency of these heartbeat requests. And we would expect our latency graphs to also be boring. We want very boring graphs. This is actually what our latency graphs look like currently. Very boring, really great, predictable. But back a few weeks after launch, we saw this happen, and this was very puzzling and concerning. We see at the very beginning of time, this is about a 12-hour window, heartbeats, the latencies, the percentiles here are looking good. And then suddenly the 95th percentile starts to peel off and get higher and higher. We saw that, we're like, okay, that's not desirable, but it's only a portion of our population. Maybe there's something wrong with a few eros. But then, some number of hours later, the 75th percentile peels off. We're like, okay, now we're noticing a pattern here. This isn't good. And then very shortly after that, the 50th percentile starts to go crazy. This is when we start to maybe panic a little bit. When we zoomed in on this graph and looked at it over just a 3-minute period, we see a much different picture. We see latency is looking really good for a short period of time, and then suddenly this huge spike in latency. And as you may notice, these spikes in latencies are actually very predictable. They happen at a very predictable interval. So the question is what's going on here? if we see something like this, we deal with computers that are very repetitive and do things predictably. So there's some process happening here by which it's causing these latency spikes. We then looked at a graph of, you see the green line here is the kind of heartbeat distribution, the heartbeat count, and the other colored lines are latencies. We see here, actually the heartbeat counts are beginning to not be very uniform. They're starting to show some periodicity. Suddenly we have this huge latency event, and then after that, our heartbeats become even more spiky. So some latency in the system is causing heartbeats to synchronize with each other. There's some hidden beam that these eros are attached to that they're somehow able to influence each other and kind of get on the same page or same schedule. And as time went on, our heartbeat distribution started to look like this. We'd have massive spike in requests, and then a drop, and then a little bump, and then another peak, and then a massive peak, and then a little bump. Our heartbeat count graph actually started to look like a heartbeat. It was crazy. So our system was suffering a heart attack. And at the core of it was some actually pretty benign logic on the surface. This is a gross oversimplification of some code that we have on our device that's like, okay, there's a process that heartbeats to our cloud. Cool. While we're not done, send a heartbeat, sleep for some amount of time, and loop. Dead simple. But herein, lies the problem. There is a shared beam here where eros are being affected. Any ideas? Right there, that's a blocking call. Basically, this call is saying, wait for the server to tell me to continue. What we were seeing on the back end with those huge latency spikes was our system blocking. We actually encountered this in multiple ways. We had multiple shared beams, so to speak. But one of the most prevalent was garbage collection. We all, or most of us probably work with the JVM and are familiar with garbage collection. And we may be familiar with these kind of stop the world garbage collection events, where the JVM's like, I really need some memory, pause all threads in the system while I go and reclaim this data. Well, as you can imagine, if we're handling a bunch of heartbeats and we stop all threads, those heartbeats are suddenly in limbo, no longer being processed. And even though we've stopped processing those heartbeats, all the other eros out there have not stopped heartbeating. They're continuing on their merry way saying, hey, I need to tell you that I'm alive. So suddenly these heartbeats come in, and Netty underneath is accepting new connections and saying, okay, we're going to process your request. But the JVM is like, nope, sorry, I'm collecting garbage, wait. And then finally, when the JVM is done collecting garbage, it's free to process all the heartbeats, the ones that were currently in flight and all these ones that have been queued, and they get processed and returned very quickly because they're very simple requests, and they all return at the same time. And they all return, well, not at the same time, but very close together. And then those eros get the response and then sleep. So as time went on, as we had more of these latency events, more and more eros were getting caught up in this wave. And so especially when you have a massive influx of requests, you're having a sudden spike in utilization of resources, which, surprise, might cause more garbage collection, causing more devices to get caught up in this. And so it was through this process that eros, which had previously been uniformly distributed, had found this shared beam by which they can influence each other, which is the JVM garbage collector or thread pools. Oftentimes it was thread pools that came into play, although it wasn't always garbage collection. Database latency and behavior in our database also had effects here. So now that we have our bot army working together in unison, what better way to make your team do even better than giving them positive feedback? And so by positive feedback here, I mean feedback loops. I want to talk about behaviors in our system that start off small, but then slowly grow over time as the system kind of interacts with itself. Some of you may have seen something like this. This is called a bird murmuration. It's when you have flocks of like thousands of birds all flying together. And if you watch them, they all seem to move in unison and make these kind of sometimes random choices. But they all move together, at least it looks that way. And it doesn't look like there's any single bird leading the flock. And it was only kind of with the recent advent of high-speed film that scientists could study the behavior of these flocks. And what they saw was that each bird was kind of operating on its own, but it was taking cues from the other birds in the flock, its nearest neighbors. And so as its neighbors moved, the bird would kind of like adjust itself according to those birds, and these movements would spread very rapidly throughout the entire system. In our worlds, we have different kinds of flocks. We have microservices. And sometimes we have systems of hundreds or even thousands of microservices. And microservices are not always like these very lone. We design them to be like these things that have their own set of responsibilities, that provide their own functionality. But microservices oftentimes take dependencies on neighbors. They're getting requests from this service, they're calling to that database, they're storing stuff in this cache, they're calling some other service to like process or enrich data. And so we have like these very coupled graphs of systems. And depending on how you set it up, these graphs could be tightly coupled, very tightly coupled. Latency in one system can cause latency in another. Failure in one can cause failure in another. An influx of requests in one place can suddenly explode into a lot of traffic throughout your entire system. And so the more dependencies we have and the tighter these couplings, it starts to take on this behavior of this flock where the small movements of one can kind of propagate out through your entire system. At Eero, we like to detect events happening in networks to kind of benefit our customers. One of those types of events is a network going offline. If we detect that your network is offline, we want to send actually a push notification to your mobile device because if your network's offline, good chance you're sitting there watching Netflix and suddenly things start buffering or going dead and you're like, what happened to my network? And you open up the Eero app and we want to say, your network is offline because of this. And that's usually fine. We detect these events. We send a push notification. And the mobile app calls the cloud to say, hey, what's going on? Give me the deets on my network. And generally, that's kind of where the story ends. But sometimes there are big enough events where we detect a lot of change. This could be an ISP outage. This could be a power outage where many networks are going offline at once. And we send out a lot of push notifications. And a lot of requests come into our cloud. And it could be that we have a service not behaving properly, and this leads to some errors. Now again, oftentimes, this is where the story ends. We design our systems to handle errors and to be resilient and to recover. But if the event is big enough and the nature of this error is such that it can cause problems in our system, a very specific example for us is these errors suddenly disrupting our API tier that the devices talk to. Now, if the devices are having a hard time heartbeating, and heartbeating is a way that we know that Eeros are online, suddenly we might be getting some false positives about Eeros falling offline, which means we're detecting more events, and we're sending out more push notifications, and we're getting more interference. Our database CPU might be going up, queries might be getting slower, our load balancers might be having trouble keeping up with this sudden influx. And this loop can go around a few times, and then finally, this leads to a fire, and we're not happy. So these positive feedback loops can occur in a lot of ways, and it's, we think back to a lot of the talks we've seen, it's this imperative style where a service is saying, I need this data, I need this now, give it to me, and a service has nothing else to do other than try to respond or fail. And if we don't think about our services in a way of being kind of autonomous and self-governing, these failures are more likely to propagate. So step 3, we've got things working together, we've given them feedback, got these nice feedback loops going, so the next thing to do is to fail. And I don't mean just failure in one place, I mean cascading failure. The domino effect, or you might even liken it to the butterfly effect, where one thing falls and knocks the next thing down and so on until finally all your dominoes are down and nothing is working. So I'd like to talk about a kind of a well-known cascading failure case. Apologies to those who went to the ACA anti-patterns talk. This may be review. But this is a diagram of the Titanic. This is a well-known case of cascading failures. And at the time it was built, the Titanic was thought to be an unsinkable ship. And it wasn't just because it was the biggest moving object, that humankind had ever built. That's like saying my service is not going to go down because I have the biggest server you've ever seen. That might be true if you could get a really big server, but probably not. The Titanic actually had some very modern hull design for its day and age. It was divided into 16 watertight compartments, which you can kind of see divided by these thick black lines, which are called bulkheads. And the idea was that if there was a breach in the hull, if there was failure in some part of the ship, that part of the ship would flood, but the flooding would be contained to that section of the ship. And they figured that as long as the ship had at least 4 watertight compartments kind of unharmed, the ship could stay afloat. So the Titanic was built to be resilient to failure. It had this in mind. It wanted to not have the ship sink. But as we all know, it sank. It sank because it hit an iceberg and its hull ruptured. So why? Well, when the boat struck the iceberg, it actually tore a hole in the front of the ship that ruptured 3 of the watertight compartments. And so the front of the ship started filling with water, but only the front part, which was as planned. But what was perhaps unanticipated was that rupture and that filling of the front of the ship caused the bow to slowly sink underwater. And while the bulkhead walls were watertight horizontally across the ship, vertically, they only extended several feet above the waterline. So as the front of the ship went lower and lower, suddenly the water flooded in and was able to spill over these bulkhead walls into the untouched compartments. As those filled up, the front of the ship continued to sink lower and lower, so this failure starting to cascade over into other parts of the boat. Eventually, the front got so low that the rear end of the ship lifted out of the water. Now, in the back of the ship, there's some pretty big things. There's the engines, which are extremely heavy, and these propellers. The boat was never designed to support the engines and propellers being suspended outside of the water. The ship was being subjected to stress and use that was never planned for. And so this stress eventually caused the midsection of the ship to fail, and the ship broke in half. We went from a rupture in the front of the boat, which is a planned failure, to a ship being torn in half, the largest ship ever made being torn in half. That is an extreme case of cascading failure. This is kind of a simplification of load balancers sending traffic to backend services. Thankfully, when we think about failure, it's not in the context of human lives, so I'm happy to have that kind of job. And we have load balancers because we want to tolerate failure in backend services. And we have multiple load balancers because we want to tolerate failure in our load balancing tier. And I want to talk about an instance where we had some cascading failure in this case. So, not abnormal. There's a problem in a system. Its health check starts failing. Normal operation would be load balancer stops sending it traffic. But in this case, we had a misconfiguration in our load balancing tier. The load balancer's health check was mistakenly also pulling in the health check of this backend service. So while the service was down, the load balancer was completely healthy, but we thought it was unhealthy. So our service goes down, and suddenly health check fails, and now load balancer health check fails. Even though it's healthy, we think it's down, and so it no longer routes traffic. Again, in a normal case, this is a sad mistake to make, but we have 2 more load balancers. We should be fine. I mean, we give 3, but we know that 2 can handle the traffic. And so they pick up traffic. They take on the extra traffic. Now it's these backend services that are receiving the traffic. And in a normal kind of steady state configuration, this would be totally fine in our system. But we didn't anticipate a side effect of this failure. And the side effect was one of the load balancers lost all of its connections. Those connections have to go somewhere. So they're going to go to the remaining ones. In our case, we use TLS or SSL between devices in our load balancing tier, We want to keep your data secure. But setting up a TLS connection is actually pretty expensive. We also use client certificates, so there's some extra crypto going on there to validate identities. So this sudden influx of connections spikes our CPU to 100%. And when a load balancer is at 100% CPU, that means connections are going to get dropped, it's going to have problems. That load balancer's connections, health check might also actually start to fail because of this extreme amount of load. So it goes on fire. It goes unavailable, its connections drop. Well, we have one last hope, one more load balancer to take on everything, and maybe this is enough. Maybe we've provisioned our system to handle all these connections, but we just went through this. This influx of connections has suddenly become a thundering herd. Meanwhile, the fire's gone out on the last one because it's no longer serving connections. It's healthy. It's like, I'm back, I'm not serving any connections, my CPU's recovered, I'm here to save the day. It takes on some traffic, but it's too late. This one has caught on fire, drops out, and the cycle repeats. This cascading failure is a vicious cycle of whack-a-mole. And our load balancing tier is now out. Service has been denied. Long before this, the pagers have been going off, and we're trying to handle things and figure out what's going on and how can we kind of staunch the tide. I want to let all you Eero customers know, rest assured, you can still get Wi-Fi even when our cloud's having trouble. We've isolated failure. Like, your Wi-Fi is not going to be broken. You just might have some trouble getting up-to-date information about your connected devices. So those were kind of 3 steps or 3 examples of how we experience failure in our system. I'd like to talk a little bit about ways you can potentially avoid these scenarios. So how not to DDoS yourself. And step 1 is to be a little random. We talked about synchronicity and how even with our best intentions, with randomness in our external environment, things had a way of coming together and working together. So how do we counteract that? If we kind of revisit that heartbeat code, here is, again, a simplification, but gets the idea across about how we address this, at least from the client side. 1, this first step here is let's avoid global synchronizing events. Like I said, people set things up at different times, but actually there are these global events that can cause synchronization. Power outages. All devices kind of come back online as power is restored. ISP outages. A lot of people get internet back at the same time. So we wanted to do a little wait here just to spread things out a little bit in case we're encountering one of those events. And then the other thing we do here is actually it's not introducing randomness, it's actually introducing strict rigidity. No matter how long this blocking call takes, we're going to enforce that this device heartbeats at the expected interval and not allow any, this is kind of like removing the beam. No matter how long or how much latency is happening on the server, there's no way that latency can now affect the way this device behaves. Step 2, be reactive. We're at the Reactive Summit. There's been a lot of great discussion here about reactive principles. When we think about message-driven architectures, back pressure, these are architecture and design considerations that can really start to fight these feedback loops. We want to, if we're message-driven and event-driven and we have back pressure, a system has better control over its own behavior. It's no longer this imperative case where an incoming request kind of demands that work be done. We can feed off message queues. We can tell requesters of our service to slow down in case we detect our system starting to degrade. It enables us to build, again, these very massively distributed services with many microservices inside, but in a way that they're more loosely coupled and less likely to be kind of jerked around by the flock. On our side, we've implemented a lot of fail-safes. We use things like the circuit breaker pattern. We have some configurations that we can play with to kind of cut off traffic to entire services if we notice things are starting to escalate out of control. And then slowly ramp that traffic back up to restore behavior to a normal state. And finally, step 3, isolate failure. And this one is actually, it's pretty difficult. Because in the HA proxy case, and in the case of the Titanic, that was the goal. The goal was to isolate failure so that a hull rupture in one part of the system or a load balancer coming down in our system wouldn't affect other parts. But when we're faced with a failure, and we're faced with this concept or this possibility of cascading failure, we have to really make a hard decision about what happens when things fail. In the case of the load balancer, we're actually trying to recover from failure. We're saying, this system has gone down, but you know what? We're going to make everything OK, because you can all go over here. This part of the system is working. So we try to recover quickly and restore service to our customers or our devices. What was interesting about the Titanic case is had the system failed in a more even way, had they had no bulkheads whatsoever, the ship still would have sunk. But it would have filled with water in a uniform way. It would have sunk much more slowly. It never would have split in half. And it probably would have taken long enough that other boats in the area could have come to the rescue. In our HA proxy case, we could have adopted another failure pattern. We could have said, well, all the clients that were talking to the HA proxy that failed, you're out of luck. You're just going to have to deal with failure for now. Everyone else, you're lucky. Those load balancers are fine, and then we can come in and rescue the system. So do we want to auto-heal and potentially have pathological behavior in one part of the system bleed into the other part of the system? Or do we want to isolate failure completely and let it continue to fail and rely on some other mechanism to bring things back to a stable state? So our conclusion here, we design our systems with failure in mind, and we try to anticipate everything. But oftentimes there are, when we get that page in the middle of the night, it's because there's something that we haven't anticipated. There's something new. And I hope from this talk, you've gotten a little bit of more of an insight into how things can fail, and maybe some thoughts about how you can, at least if you're dealing with a failure, think about it and reason about it, or hopefully avoid failure in the future. Thank you.